Good morning. We were discussing the reheat cycle, the concept of reheat in a steam power plant or in Rankine cycle last class. Now the concept originated from the fact that an increase in the mean temperature of heat addition in any cycle, heat engine cycle, increases the thermal efficiency of the cycle and also the thermal efficiency of the plant where this cycle is the theoretical cycle. Now in this regard we first thought that if we increase the maximum temperature of the cycle in a Rankine cycle, that is the temperature at the end of the heating process in the boiler or at the entry to the turbine, then obviously the mean temperature of heat addition will increase. But there is a limit to this maximum temperature of the cycle which comes from the consideration of the turbine blade materials. That means the turbine inlet temperature cannot exceed certain value, so that we have to restrict it to a maximum temperature to the cycle, that is the turbine inlet temperature. So keeping that temperature fixed, still we can increase the mean temperature of heat addition if we increase the temperature of that part of the heat addition which is the sensible heat to the liquid and also the heat which is given to the liquid for change of phase and then superheat to the fixed maximum temperature by increasing the boiler pressure. That means if we increase the boiler pressure, okay, and if we heat the water at that high pressure to vaporize to the steam and superheat to the same maximum temperature, then also the average temperature of heat addition increase. That was discussed earlier. But what happened to that, this was also discussed, that if we do so, we will see that the expansion process comes up or ends up to a point where the dryness fraction decreases, or during the entire expansion process the dryness fraction is on an average much lower than that corresponding to the case when the pressure, boiler pressure is lower. That means if we increase the boiler pressure keeping the maximum temperature fixed, okay, we increase the average temperature of heat addition, but at the same time the dryness fraction in the expansion process in the turbine at any pressure is reduced, and finally we will end up to the end of the expansion process a dryness fraction which may be lower than which is required. That restriction comes also from the turbine blade materials. The turbine blade materials cannot have a dryness fraction lower than some value which is usually 0.85, 0.8 to 0.85, below which the corrosion and erosion problem of the blade come into picture. So to overcome this, we considered that okay, we can use the high pressure, that means we can increase the boiler pressure, but we go to the concept of reheat. That means we consider the expansion in the turbine in two stages. In one stage the expansion takes place from the initial pressure, that is the boiler pressure, to an intermediate pressure, not to the condenser pressure. That stage is known as high pressure turbine. Then the steam which is at the exit of the high pressure turbine at an intermediate pressure is again heated at that constant pressure, that intermediate pressure, to a temperature usually to the initial temperature of the steam, and then again it is expanded in another stage of turbine or low pressure turbine stage where it is expanded to the condenser pressure. And we have seen in the cycle diagram, Rankine cycle diagram in TS plot or HS plot, that this ensures a high dryness fraction within the allowable limit at the end of the expansion process. This thing we discussed thoroughly in the last class. So as a continuation of that, today we will first solve a problem and then I will go to another aspect, regeneration. This example will clear that thing. In a reheat cycle, steam at 500 degrees Celsius, expands in a HP turbine. So it is only given that steam temperature, not the pressure, till it is saturated vapor. That means it is expanded in an HP turbine till it is saturated vapor. It is reheated at constant pressure to 400 degrees Celsius. Means it is reheated at constant pressure to 400 degrees Celsius and then expands in a LP turbine to 40 degrees Celsius. This is the temperature of the condenser. That means the condenser pressure is the saturation pressure corresponding to this. Boiler pressure we don't know, there may be a superheated steam, so boiler pressure we don't know. And then expands in LP turbine to 40 degrees Celsius. If the maximum moisture content at the turbine exhaust is limited to 15%, that means the corresponding dryness fraction is 85%, 0.85. What are the things to be found out? The reheat pressure, that the pressure at which reheat was done, the pressure of steam at inlet to the HP turbine. What was the pressure of this steam? That is definitely not the saturation corresponding to this temperature. Why? Because steam is not disaturated, steam is superheated. That means the saturation pressure will be the pressure at the boiler will be the saturation pressure corresponding to the temperature at which the steam was vaporized. The net specific work output, the cycle efficiency, assume all ideal processes, means assume a Rankine cycle. We have taken this data. So how to solve this problem? Please write it. I repeat again, the steam, first of all, these are the pertinent points. You take the steam entry, that inlet temperature is 500 degrees Celsius, that means T1, the point 1 in the Rankine cycle. Then reheated at constant pressure. Now this reheat is done not up to the initial temperature, 400 degrees Celsius, and then expands in a LP turbine to 40 degrees Celsius. Well, if the maximum moisture content, now these are the three important data. Maximum moisture content is 15%, that is also important. Then we will have to find out reheat pressure, the pressure of steam at the inlet to the HP turbine, the net specific work output, the cycle efficiency. Fine. Now to do this, what we require is that we better draw the TS diagram first. You understand? The TS diagram first. Let us draw the TS diagram. What is this? TS diagram will tell this thing very clearly. That means this is the inlet point 1. Then it is reheated. This is the intermediate reheat pressure. That means this is the P1. So this is 2 and this point is 2. Then it is reheated to a temperature which is not same as that. This is the 500 degrees Celsius. So this is 400 degrees Celsius. Then it is expanded down to the condenser pressure. This is the condenser pressure. Simple problem, condenser pressure. So this part remains the same. This is the pressure line, boiler pressure P1 line. So this is 4, and this 4 is such that it passes through the x is equal to 0.85. That means this point is fixed. So let this is 4, then this is 5, then this is 6. So 6 to 1 is the boiler pressure, constant pressure heating represents the boiler heating. Well, so here it is heated, heat is added, which is the boiler, from the boiler, that is QB. Now 1 to 2 takes place in the first stage of high pressure turbine. This is the reheat pressure. Then it is reheated. So here also heat is added. We denote it as QR, that is the heat for the reheat. So this is a heat addition process at constant pressure which occurs in the reheater. Is a coil placed in the boiler which takes the heat from the flue gases, burnt products of combustion, fuel, and it is heated up to a temperature. T2 is less than T3, so T3 will be 400. This is given. So then it is expanded to the 0.4, which ends up to 0.85 drainage fraction. This is the condenser pressure. So P4 is the condenser pressure. P4 is the condenser pressure. What are the data given? Data given, T1 is 500 degrees Celsius, T2 is 400 degrees, T3 is 400 degrees Celsius, T4 is 40 degrees Celsius, and X is 0.85. First of all, we will have to find out the reheat pressure. How to find out the reheat pressure? Now if you see the steam table, then it is, you know the point, the entropy of this point you know, because you know the drainage fraction. At this 40 degrees Celsius temperature, you see the saturated steam table, then you can find out these 2 points entropy, and accordingly weighted average of these two with X will give you the entropy here. That means S4 is equals to S3. So therefore you will have to look in the table of superheated steam or superheated steam table that at 400 degrees Celsius which pressure equates this value of, gives this value of the entropy. You understand? Geometrically you see that this is the pressure. Geometrically if the pressure lines are there in TS plot, if you have a TS diagram, then you can find out this pressure. Okay, so you know the point 3. How to know the point pressure, this pressure? So you can now heat to at constant pressure to the point 2 in the reheater. in the reheated pressure to the saturated condition. So therefore, what you know is the entropy at this pressure. That means when you know this pressure fixed, so at this pressure from the saturated steam table you know S2. If you have got any difficulty, you tell me. Then you set S2 is S1. Obviously, then you find from the steam table at which pressure in the superheated steam, for the superheated steam at 500 degrees Celsius give this entropy. So geometrically things are very clear, but to find out from the steam table you may have to do little trial and error to find out these things, which will be difficult, little difficult. So therefore, always this type of problem is preferred to be solved with the use of Mollier diagram or HS diagram, which I discussed in the last class. That let us consider the HS diagram. HS diagram looks like this. Again I repeat, this is the x is equal to 1 line, and we have got x is equal to 0.9. So we have got let x is equal to 0.85, which I want now, like that different x lines are there. This is actually originating from this critical point. Now these are the constant pressure lines, these are the constant pressure lines, these are the diverging line, constant pressure line, diverging line, these are the constant pressure line, these are the constant pressure lines, sorry, and this is P constant, these lines are P is equal to constant. These are the important lines in HS diagram which you require, and these are the constant temperature lines, these are the which always like this, which always meets this curve, a part of the curve I am showing at this point, and so that the constant pressure line matches with the constant temperature line in the vapor dome, as you know. So now this is very simple, 40 degrees Celsius and this dryness fraction 0.85. So how do you find out this? You take the 40 degrees Celsius. For example, I just tell you that this is the 40 degrees Celsius isotherm. So this cuts here, this point. So this pressure and temperature, they are constant pressure temperature line. If you see the constant pressure line which runs like this pressure may be equal to 0.08 bar approximately, or 0.1 bar, which is the saturation pressure corresponding to this temperature. That means this is the condenser pressure. So this pressure cuts here. So therefore, I have the 0.4 here. I have the 0.4 here, for which entropy is directly found from the abscissa. You don't have to calculate it. So enthalpy is directly found in the ordinate. So this is the point. Now I have to go vertical. That means HS diagram, constant entropy process means the vertical line upwards. And here I know the temperature. That means if I go up, let this is the 400 degree Celsius temperature line. So therefore this is my point 3. That means I am generating the cycle in HS diagram. That is the only thing. But it is not a plain paper the way I do HS diagram and show only the processes that I require, but they are constant pressure line, constant temperature line, all these things are there. That means in a graph paper you plot the process. Very classical method and very simple method. So we know the 3. So therefore how do I know? The reheat pressure, this temperature 3 cuts here, somewhere here. Actually there is something, actually this diagram should be like this, otherwise this looks odd. Okay, I just change this diagram. So this is the, I am sorry, so this is the constant temperature line. So okay, now this is all right, let it be like this. Okay, whatever is there we have to think, because the diagram is not very proportionate in just geometry, however doesn't matter. So this cut, so therefore I know this point, so therefore this is the reheat pressure, that means this pressure is P2. Now I cool it at constant pressure, that means I can read the point where it cuts a isobar line, that means this point cuts this 400 degrees, so this point is P. So through this point there is an isobar passing, so this isobar is P2. Now to generate the point 2, I will move along this isobar to come to this point 2, that means 3, 2. So these are the process. My geometrical drawing is such, this was very steep, actually this is not this much steep, however understanding is more important. So from 2 again I go up and cut the 500. So this is 400, let this is 500. So this is my point 1. So the isobar which runs from this point, let this is the isobar which runs at this point. So this is my pressure P1. So I know the pressure P1, I know the pressure P2. Alright, enthalpy and entropies are found. So the rest part is very simple. When you find all this, that means you can draw this this portion of this curve in the HS diagram or Molière diagram. Then you know everything, you can find out the net specific work output. Net specific work output will be H1 minus H2, that is the work output in the high pressure turbine, plus H3 minus H4, and which are directly read from this ordinate enthalpy. Net specific work output, the cycle efficiency, this is the net work output, and the heat added. Heat added is H1 minus H6 plus H3 minus H2. So H3 minus H2, H1 minus H6, which is not there in this diagram. This is very simple, you can find out H6 considering this pump work. I have already told that how to find out H6, because H6 minus H5 is P5, sorry, V5 into P6 minus P5. P5 is the condenser pressure, that means this pressure, saturated pressure corresponding to this, and P6 is P1, that means P1. So that means this has been found out by the application of steady flow energy equations and considering the process to be isentropic and the water is incompressible, so that specific volume between 6 and 5 remains almost the same. This has been discussed earlier, so you get everything. That means this part of the cycle diagram is generated here. So it is always preferable to work out this type of problem in HS diagram, though you are conceptually alright, but sometimes to find out from the steam table to the pressure P1, P2 will be little difficult because you will have to do some trial error method. Okay? So this gives the clear concept of reheat. Now we will come to the concept of regeneration. What is regeneration? Concept of regeneration. Let us write this thing. It is very, very important. Concept of regeneration. Before coming to the concept of regeneration, I must first discuss the basic Rankine cycle again in diagram. This is the TS diagram of the Rankine cycle. Let us consider the dry saturated steam for the time being. Let us consider. It may be superheated steam, but for simplicity we draw the dry saturated steam at the entry. And now I draw the basic Rankine cycle 1, 2, 3, 4, 1. Now, what is concept of regeneration? Again, the concept of regeneration comes in consideration of the increase of thermal efficiency by increasing the average temperature of heat addition. Now you see the average temperature of heat addition, now heat addition is some temperature from 1 to 4, okay, and the total heat added is represented by this area, is always represented by the area of 1,4 under S axis. That means this is A, this is B. That means the area 1AB4 is the amount of heat added, and this area, that means this area. This area is the heat added area, and this is heat is added during the process 4 to 1. Again repeat. And the heat rejection is the area 2AB3, because heat is rejected during the process 2 to 3. Heat is rejected during the process 2 to 3. Well, so heat is rejected during the process 2 to 3. This is the heat added, and this is the heat without reheat. Now this is the heat, this area, so this area 2AB3 is the heat rejected. Now you see, while we discussed first the increase in the mean temperature of heat addition, what we did, we increased the inlet temperature, that means the maximum temperature of the cycle, which was increased like that, the superheated domain, but there was a maximum temperature fixed. Or what we did, we go with a different higher boiler pressure. Try to understand, I am not drawing it. That means 4 point will go somewhere here, there is another pressure line, so that we can increase the mean temperature of heat addition, because the range of temperature for the heat addition is increased. But another way we can increase the mean temperature of heat addition. What is that? If you observe this heat addition process, you see the basic difference from this cycle with the Carnot cycle is that a very less portion of heat is added at the maximum temperature. So heat is added distributedly from temperature 4 to 1. Now if you somehow can heat the water at its lower temperature, for example in the lower temperature range from 4 to somewhere here, for example, somewhere here. Let us consider this saturated temperature. Let us consider this temperature at 5, 4 to 5. You understand? 5 is the saturated state at that pressure. This is the subcooled state. That means the sensible heating part of the liquid, if can be taken from the heat generated internally, that means the heat of the cycle. That means if you can take the heat from the hot steam while flowing through this process, that expansion process, and can somehow make an arrangement to transfer that heat internally from the cycle to heat this liquid, for example from 4 to 5, then only I have to add heat in the process 5 to 1, which is at constant temperature, and in that case it becomes equal to a Carnot cycle because heat is added at the maximum temperature of this cycle. So the average temperature of heat addition is T1 and the temperature of heat rejection is T2. So efficiency is 1 minus T2 by T1. And basic philosophy is that even if we cannot go up to 5, we can go up to this. That also is alright. That means if we can heat up the water in its lower range of temperature by utilizing the heat of the system in some other part where the system is hot, that is the internal, if we can use the heat. By doing so, what happens if you can make the range of temperatures higher? That means if we heat up to this, then the mean temperature will be something between T1 to this point, which is definitely higher than T1 to T4. And if we can go up to this point, then verifying the mean temperature of heat addition is T1 only, that is the maximum temperature. So if you do so, then the average temperature of heat addition is increased, and in a limiting or ideal case, if we can do up to 5, then the process, the cycle becomes almost or identically a Carnot cycle. So this concept is known as regeneration. That means we heat it internally. This part of the heat addition is done internally by utilizing the heat of the system in the cycle itself. This is the concept of regeneration. Okay, how it is done? First of all, to understand regeneration, we have to, well, go through this. Now, what is done in regeneration? Before that, I just draw this diagram first, otherwise it will be difficult for you to understand here. Now, if I draw, well, here itself, this diagram, a regeneration is done like this, that if you consider this way, this boiler, here, before that, let us consider the diagram like this. This is the boiler. Well, this goes to the turbine. Let one stage of turbine. This goes to a turbine where it comes and goes to the condenser. Well, this is the circulating water, goes to the condenser. Then what happens is that the feed pump is here. I will explain this thing first of all. Now, if I place, theoretically I consider, which is not possible after all. Now, first of all, you have to understand the thing theoretically. A heat exchanger, that means this feed water is being heated and then we give it to the boiler. That means what I do, try to understand one, that means the turbine inlet steam which is being expanded, okay, to the point 2, then it is being condensed to the point 3, that is in the condenser, heat is taken away by the circulating water, then the feed pump heats this to 4, then I don't heat this water, that means if I feed this water 4 to the boiler, what will happen? That means I will have to heat up from the point 4 to 5, but instead of that, if I place this water through a coil placed in the turbine where the steam expanded and steam is expanded and let the heat transfer to take place between the steam and the water, so that water takes the heat from the steam, the entire turbine is insulated, there is no heat transfer with any third body outside. Then water is heated and I consider the water to be heated at the point 5, 4, 5, that means which I wanted, that means let the water be heated up to its saturation temperature corresponding to the boiler pressure, so that it enters the boiler at the state 5 instead of 4. Difference is that they are at the same pressure, but 4 is at subcooled state and this is at a temperature equals to the saturated temperature, that means a saturated state. That means the sensible heating is done here, and then I give the heat. That means this heat addition to the boiler is equals to Q51, that means from 5 to 1, and it gives only the latent heat, that means at constant temperature heat addition. So this is the block diagram of the component that we envisage this way. But question immediately comes, how can I put whether a coil of this type as a heat exchanger can be put into a turbine that comes afterwards? Definitely no. But to understand the concept or the philosophy of this regeneration, we think as if the water is allowed to pass through the tubes or through the condenser where it can exchange the heat directly to the expanding steam to be heated to a temperature 5 and then comes to the boiler. Okay. So this is conceived in a regeneration, ideal regeneration process. This is now shown in an expanded view like this, where let me draw the diagram first. This is the TS diagram. This is the TS diagram. Well, okay. So now this is the vapor dome in TS diagram. Sorry. Vapor dome in the TS diagram. Let the point is like this. Let me first draw the basic Rankine cycle. That means this is my point 1, this is my point 1, this is my point 2, this is my point 3, this is my point 4. So let me draw the basic Rankine cycle like this. This was the basic Rankine cycle. Vis-a-vis, now I conceive this way, that if this be the turbine, we consider a reversible heat transfer between this. That means when I consider is these two, of course you do not confuse with these two, otherwise these two will represent actually 1 to 2. No, this 2 is all right, 2, 3, 3 is all right, 2, no, this 2 is all right, 3 is all right, 3 to 4 is all right, yes, 4 to 5, all right, everything is all right, everything is all right. Now you see, now if we consider this process of heat transfer through this, between the steam and water, feed water, to be reversible, how we can conceive? This is very important. This is not given in any book. Again I am telling that let us consider this is the steam path. Let us consider this is the steam path. Let us consider this is the steam path. And let us consider this is the water. This is the water. They are flowing in the counter flow directions. Now at each and every point, there is an heat transfer. That means heat is transferred from the steam. As it expands in this direction, steam flow. How to conceive it? This direction, steam flow. And this direction, let us consider water flow, just for our understanding. As the steam flows in this direction, the pressure of the steam is changing, is decreased, but water flows at a constant pressure. But across this, there is a temperature difference which is infinite small at any pressure. That means at any section, so that a reversible heat transfer takes place. That means when water flows in this direction, it gets heated. That means there is an increase in temperature, while steam flow in this direction, there is a decrease in temperature. You understand? And each and every point, there is an infinite small temperature difference, so that the water is getting heated or steam is losing heat reversibly. For an example, let us see here, the steam from the inlet has expanded to this pressure and then it exchanges heat. These divisions are infinite numbers. That means we have to consider in terms of infinite number divisions of pressure. So for an infinite small such process, the heat is transferred, and because of which the water changes or increases its temperature from this point to this point. This is explained here now. What is done? Now, if you divide now this into different pressures, just like so, infinite number of pressures in a infinite small divisions. Now these are the pressures. Okay. Now we assume like this, the steam part expands up to some pressure, and then if it heats the water, for example water is here. So this steam gives heat to the water from, so that it reaches its temperature from this point to 5. Try to understand, this is very infinite small difference, that pressure. For example, I am showing in such a, for clarity, the big difference. So if the steam has to give the heat to this water to be heated, then steam will be condensed. Try to understand, steam will be condensed at, sorry, here at some position. That means steam is condensed like this. So therefore, a steam at here will be condensed to some extent at that temperature, where water at that temperature will take the heat and will raise this temperature. So during the heat transfer, water temperature will rise. So you can ask me that the temperature difference will be there, but this temperature difference is so small that if you consider into infinite small division, so there will be always a delta T temperature difference for the heat flow. Similarly, the steam will condense from now this portion, expanded from this portion and come to this pressure, and where it will condense here to heat the water which is coming at this point to get this temperature. Similar way, the steam will expand to this pressure and it has to condense at this pressure to this point, so that the water here will be taken the heat and go to this temperature. Again, what will happen? Steam is condensed to this, expanded to this pressure and then again condensed up to this point, so that water which reaches here, which I consider the inlet temperature of the water, it is flowing in the counter flow direction, which will be heated up to this. So therefore we see the steam flows in a zigzag way. So if we connect this terminal point, we get a line like this. That means if I denote this line as 1, 2 dash, what does it indicate? This is the actual expansion process of the steam, which is not isentropic. Why? Because it transfers heat. That means steam as a working fluid, I can tell this suffers a process, a diabatic process, which is a reversible heat transfer process. That means it is a reversible process, but heat transfer process, not an adiabatic process. So therefore it is a reversible diabatic process. That means which is 1 to 2 dash. That means the exact expansion of steam from 1 to 2 is now replaced by 1 to 2 dash. Then from 2 dash this becomes the isentropic. So therefore let this point is 2 dash again. So this point let as 3 dash. So therefore the entire expansion in the turbine can be conceived of 1 to 2 dash, a reversible heat transfer process. Heat transfer, why? The heat is given to the water, feed water. Then 2 dash to 3 dash is the isentropic process. This side, whereas the water side, now if you see the water side, the cycle is very simple. 3 to 4 is the feed pump. Then from 4 to 5 the water is being heated by the steam, 4 to 5, and therefore we see the entire heat taken in this process of 4 to 5 is coming from this steam between 1 to 2 dash process. Now it can be shown. So therefore the external heat addition now is what? External heat addition is now, therefore the external heat addition, I can use a different pen, that heat addition, external heat addition is this is. So this is the QB. Now this equals to QB. Now you see that it can be shown that these two lines are parallel. These two lines, this line 5 and 1 and 2 dash and 5 and 4 are parallel to each other. How we can show it? Now you see the delta T is very small. So at each and any step, let us consider these two steps. The rise in delta T, steam side, this is steam side, becomes equal to this delta T in the water side. Obviously, because this delta T is same. That means the temperature rise for the water will be equal to the temperature rise for the steam. Moreover, during this infinite small process, as the steam goes here, flows along this direction, water flows along this direction, the entropy change is also same. That means this distance becomes equal to, if I make a projection, this distance. That means this part of the curve is parallel to this. And this way we can see that this is valid for all the parts, so that the line 1, 2 is parallel to the line 4, 5. Alright. Now you see that I can show you that therefore from the 1, 2 dash, sorry. So therefore I tell now this, now make a projection like this. Very good. Let this is A, this is B, this is C, this is D. Now see that the heat added to the water, if you have got any query, you ask me, don't talk in the class. Many a times I have told you, the outside people will see that, how the IIT students go on talking in the class. I am sorry. I have to tell you that if you cannot understand this thing, or if you feel you are not feeling interested, you can leave the class, because this thing is not only meant for you, for others also. Well, so now the heat given to the water during the 4-pipe process process 4, 5 is represented by this area in TS plane 4, 5 BA, and the heat rejected by the steam during the process 1, 2 dash, this point is given by the area 1 DC2 dash, and these two areas are equal. Obviously these lines are parallel. Now let us find out the efficiency. Now heat added QB, which I have written here, now is H1 minus H5, which is nothing T1 into S1 minus S5. This is at constant temperature. This is very simple. Now what is the heat rejection? This heat rejection is what now you tell me. Now the cycle changes from 1, 2, 3, 4, 5 to 1, 2 dash, 3 dash, 3, 4, 5. Now this is my cycle. It is a rhombus type 1, 2, 1, 2 dash. Well, this is the 2 dash, 3 dash, this is the vertical line 3 dash, 3, 4, 5. So the heat rejection is now this, because this heat is taken. So heat rejection, that means this is the heat rejected in the condenser, is it not? So heat rejection is H3 dash minus H3, which is T3. T3 means T2, because T3, T2 are same in the earlier cycle T2. So T2 into S3, my S3 dash minus S3. I am taking the positive value, already I am telling this as the heat rejection. So therefore, what is eta? Eta is 1 minus T2 into S3 dash minus S3 divided by T1 into S1 minus S5. And it can be shown that these two are equal. How? S1 minus S5 and S3 dash minus S3. Now S3 dash is S2 dash and S3 is equal to S4. Now S3 dash minus S3 is equal to S2 dash minus S4. Now S2 dash minus S4 is S1 minus S5. Why? Because these two curves are parallel. The same heat transfer has taken place. That means for these two curves I can write, try to understand, for these two curves S1 minus S2 dash, that means the decrease in entropy is the increase in entropy, because the entropy change of the universe has to be 0 in a reversible process. Okay? So therefore this equal to S5 minus S4, which tells that S2 dash minus S4 is equal to S1 minus S5. Again S2 dash minus S4 is S3 dash minus S3, because S3 dash is S2 dash, S3 is S4. So S3 dash minus S3 is S2 dash minus S4 is equal to, so S2 dash minus S4 is equal to S1 minus S5. That means if I make this equal to this one, that means if I make this S1 minus S4 is equal to S2 dash minus S4 is S1 minus S5. That means this become equal to S3 dash minus. That means this becomes is equal to S1 minus S5. So that 1 minus T2. It is very simple from the geometry. So therefore this becomes a Carnot cycle. Clear? Any problem? Geometrically also one intelligent students will be able to say, you see that if you compare the Carnot cycle, now what is the Carnot cycle? 1, 2, let us give a point here. B, C, D, let's give this point E. 1, 2, E, 5, that means this rectangle is a Carnot cycle. And Rankine cycle was 1, 2, 3, 4, 5. So from this rectangle, geometrically I am deducting this part. That means 1, 2, 3 dash, 2 dash. This part I am deducting. Whereas I am adding this part, 5, E, 3, 4. And these two parts are identical in areas. That means the rectangle is deducted, the rectangle is the Carnot cycle, is deducted by this area 1, 2, 3 dash, 2 dash, and on the other side, on this half of this rectangle, I am adding this 5, E, 3, 4. That means this area 3, 4, 5, 1, 2 dash, 3 dash is synonymous to or is identical to 1, 2, E, 5. Understand? It is equivalent to that. So that means this rhombus type cycle diagram is equivalent to the rectangular cycle diagram corresponding to the Carnot cycle. One can geometrically tell this immediately from the intelligence, but one can work out this and show that ultimately the cycle represented by 1, 2 dash 3 dash 3, 4, 5 for the regeneration cycle is same as the Carnot cycle. This process is known as Carnotizing, very important, Carnotizing the Rankine cycle. The Rankine cycle. So, with the concept of ideal regenerative process, a Rankine cycle can be Carnotized. But why it is ideal? Now I tell. Obviously, immediately it is apparent that a reversible heat transfer is not possible here. Number one. Number two, that we cannot incorporate a tube containing water into the steam turbine so that this reversible heat transfer will be there. So, these two things are not possible at all. So, we cannot have a reversible heat transfer by which the counterflow arrangement, the water will be heated to the temperature exactly at which the steam is entered. It can never happen because the heat transfer will not be defined at this point. So, it cannot attain a temperature equal to the temperature of the hot fluid. At this section the temperatures are equal. If you give an infinite long heat exchanger, you will see if you make a counterflow heat, as for simple example, a counterflow heat exchanger, hot fluid is coming to this, cold fluid is coming in this direction. You can never expect the outlet temperature of the cold fluid will be equal to the inlet temperature of the cold fluid. Just common sense you think. If you have to do that, you have to give an infinite long length of the heat exchanger. You cannot exchange heat like that, so that ultimately it will catch up to that temperature. That means it will be infinitely long. This type of concept cannot come in reality. This is the actual concept of the reversible heat transfer, which takes infinite large time, and automatically the equipment will be infinitely long. So, this cannot happen, number one. Number two is the practical difficulty that we cannot pose or we cannot incorporate a heat exchanger tube which runs into the turbine. Turbine is not a device where there is a pipe or some valves are there through which the steam is flowing and it is getting expanded and giving the mechanical work. This is not the system. To get mechanical work from the expansion of a high temperature, high pressure steam, this system is entirely different. So, in that system of turbo machinery, there is no place where I can place or I can incorporate that heat exchanger which carries liquid water. So, this cannot be made. So, this entire thing is a ideal thing, and this has been conceived to understand the basic philosophy of the process. That is why it is known as ideal regenerative system or the ideal regenerative cycle. So, in case of this ideal regeneration, that if we could have made a reversible heat transfer considering an infinite long turbine and incorporating into the turbine the coil or the tube carrying the water, and considering there is an reversible heat transfer, so that the outlet temperature of the water is the inlet temperature of the turbine, and also the turbine inlet temperature is not superheated. For a superheated Rankine cycle, you cannot Carnotize it. Superheated Rankine cycle can never be Carnotized, so that dry saturated condition, so that in those conditions, if all these conditions are fulfilled and which pertain to the ideal regenerative system, then a Rankine cycle 1, 2, 3, 4, 5 is Carnotized to 1, 2 dash 3 dash 3, 4, 5. This is known as Carnotizing the Rankine cycle, and for this ideal regenerative cycle we get the efficiency exactly equals to the Rankine cycle, Carnot cycle, though in fact Carnot cycle cannot be implemented in practice. So, this also cannot be implemented in practice. Okay? But why this has been studied, this concept leads to a situation where we can implement by some other means this regenerative heating of the feed water, so that we gain in efficiency. That I told earlier, that we may not be able to heat up to 5, but by some arrangement, irreversible heat transfer, if we can heat some part of this sensible heating part by the internal heat, then at least we can increase the mean temperature of heat addition, because the range of temperature in the range of temperature over which the external heat addition takes place is increased, so that the mean temperature of heat addition is increased. This is precisely the concept of ideal regenerative cooling. So, now I will tell you what exactly is the case for actual practice, what is done. But I think the time will not permit. What is the time left? It is 5 or 10 minutes more. So, therefore, I will not do that thing. that means the actual case what is done, but I will ask you if there is any question you can ask me regarding this. I think time left is less. Any question, please? I will entertain that better, that will be better. Please, first, let him. Yes.
So in the concept of regeneration,
yes.
the steam which enters the turbine
Yes.
is used to heat up the water.
What?
But sir, then in this case we are losing some efficiency because the
Losing some efficiency? No. So that will be explained afterwards. This is a very good question. It is a very, very good question. What we are losing? We are not losing any efficiency. Again I am telling, efficiency is a function of two temperatures, mean temperature of heat addition and mean temperature of heat rejection. When we heat the water with this steam, we do not lose the efficiency because this internal heat is used to heat up the water. Efficiency, if you think in that way, forget about the temperature. Conclusive way of telling whether efficiency is increased or decreased is to think in terms of the temperature ratios. But if you define heat efficiency from more basic equations, that efficiency is the work done by heat added. All right. Now you see, when the steam is transferring this heat to this, in this way the work done may be little reduced. Yes. But at the same time you increase the heat, decrease the heat added. That means you heat up, increase the temperature of heating. You understand? That means the heat added is now H1 minus H5, not H1 minus H4. Which is independent? It is independent of the state 5. Means if you go to state 5, then it depends, very much dependent on the state 5. Try to understand. Q is, just a minute, H1 minus H5. Okay. So how much heat added will be reduced depends upon the state H5. You understand? How much heat will be reduced depends upon the state H5. So therefore it depends upon this thing, very important, interesting question, that even if you lose the work, that will be explained afterwards. Actual case what happens, steam is bled from the turbine. So less amount of steam is flowing to the turbine throughout. Initially the steam flow rate is 1 kg, steam is bled from the turbine to heat the water. You understand? So what is happening, the steam flow rate is reduced. But in this case steam flow rate is not reduced, but steam is exchanging easy. That means the thermal energy content at this point is lower as compared to that what it was having earlier, based on which you had that query. Yes, work may be reduced, but at the same time this is reduced. So therefore you can never be conclusive if you always look from the work to heat ratio, that means the work done divided by heat added. This is a very important message to you, that afterwards also, even in the interviews, different platform, we ask this question, how do you tell that efficiency is increased? But if you start with that, it is not conclusive, because work done is reduced, but at the same time heat added is reduced, and the reduction of heat added depends upon H1 is fixed, that how close this 5 point to 1. You understand? So state 5 is very important, but therefore we cannot conclusive. Ultimately you tell probably, as I know in this case the efficiency increases, that means decrease in this is less than the decrease in this. So you have to conclude like that, but not definitely, not conclusively, not emphatically. But if you explain this from the mean temperature of heat addition, then you are conclusive. You can tell no, not probably, it is definitely increasing, and it is definite that the reduction in this is less than the reduction in this. Why? Because the mean temperature of heat addition is increased. So always define the efficiency in terms of mean temperature. Very good. This is decreased. That means the work output of the turbine is decreased. Don't consider in terms of efficiency, because turbine itself does not decide on the efficiency. Efficiency will be decided on the overall performance of the component. That means you will have to search what is the heat added, what is the heat rejected, or what is the net work output, what is the heat added. So therefore turbine may give net work output, but at the same time the decrease in the heat is much more less, and engineers are not bothered about the output. It is the efficiency. Always in our daily life we should bother with the efficiency, not with the output. That output is achieved at the cost of how much input. So it is the efficiency which matters, not the output. Okay, output can always be raised at the cost of input, but this ratio is very important. That means we will always target to increase the efficiency of a machine, so that to achieve a particular targeted output we have to spend the least amount of input. Okay, or small input, please.
Sir, in this regenerative cycle, sir, the exhaust from the turbine has less dryness fraction than the
Yes, very good. That I did not tell, this is not that important. Very good question. Yes, that is another point. In this case the dryness fraction is also reduced. But these two things are so important, are so much impracticable, that this does not come into picture. In book you will see as third point. Number one, a reversible heating of water and a reversible cooling, that a reversible heat transfer is not achieved. Number 2, it is impracticable to place a heat exchanger tube into the turbine. And number 3 is that even if I allow this process to take place, yes, the dryness fraction increases. But this is a practical limit. I don't bother with that, but still this gives a limit. Yes, the dryness fraction is reduced. That means the moisture content is increased. That is one point, because if you allow this steam to expand in this way, that means in this process of heat transfer, it ends up to a point where the dryness fraction is reduced. That is another point. Very good. So concept of regeneration is clear. Now please. Efficiency does not depend on the state 5. I am again telling the actual case. In this case, we consider this is heated up to 5. We assume it is heated up to 5. Efficiency is considered very correct. In actual, if we cannot heat up to 5, efficiency depends upon state 5. But if you consider it is heated up to state 5, efficiency is T2 minus T1. But if you cannot heat up to 5, if the state 5 is here, definitely efficiency depends upon 5. But one thing is true, if we heat at any point more than 4, efficiency is increased. That you are appreciating. Not through this, but to the average temperature of heat addition. So average of any temperature between T1 to anything more than T4 is more than the average of T1 to T4. Average of T1 to T4 is always less than the average of T1 to any temperature which is more than T4. So if any part of the sensible heating can be done by the internal heat and we can land up to any state 5 which is higher than 4 in respect of temperature, then we gain into the mean temperature of heat addition. It may be a marginal, but there is always a gain. You understand? Hello, okay. So the maximum gain, we go to the Carnot cycle. If you can heat up to the 5 point, that means the entire sensible heating is done by the internal heat. So that external heat addition is taking place only to change the phase. That means at constant temperature, which is equivalent to a Carnot cycle. Clear? Concept is clear? Okay? Okay, thank you.